In our last video, we defined limit informally. Let f of x be defined on an open interval containing c, except possibly at c itself. If f of x is arbitrarily close to the number L for all x sufficiently close to c, other than c itself, then we say that f of x approaches the limit L as x approaches c. And we ended up with these three pictures, where when the x values get close to c, the y values all got closer and closer to a number L. And I like to think of that in that kind of silly way, as from the left and the right, we're getting closer to one spot. So I want to show you some examples where a limit fails to exist, where this definition doesn't apply. The first example is what we call a step function. If I was to look at the x values in this step function, as we get close to c from the left-hand side, it would look like my y values were always some number, and I could imagine calling that L. But as I come from the right-hand side, I'm getting another value, which I would call m. Well, my definition of limit requires that the y values approach some number L, not a pair of different number L's. So this does not fit that definition. So I say the limit as x approaches c of f of x does not exist in this case. I'm going to abbreviate does not exist as D and E because I'm lazy. So for a step function, our limit fails to exist. We'll have a more formal way of saying that later on in the course, actually later on in this half week when we study section 2.4. But for right now, we'll just let that be a good notion that two different things are happening. I'm not getting a single number out. I'm going to draw a pair of pictures for this next function, this next reason. So I want to imagine this time that I have a function with a vertical asymptote. And I'm going to draw two different pictures, just have two examples of this. In either one of these pictures, the limit as x approaches c does not exist. Because to have a limit exist, my definition requires that my y values are approaching a number L. Well, as my x values get close to c, my y values in this picture are both going upwards towards positive infinity. In this picture, on one side I'm going towards positive infinity, on the other side I'm going towards minus infinity. In either case, I'm not approaching a number. And I have a feeling some of you are sitting there thinking, hey Bob, I've seen some calculus before, maybe as part of a pre-calc class, maybe as part of another calculus class. And you're saying, this picture I remember seeing someone write this. And we don't need to talk about this right now. I'm just going to put it here in case someone's having that thought. That they have seen someone write the limit as x approaches c of f of x equals infinity. Well, if you were thinking that, you have actually seen that. This is something we will actually write in this course later on. But it's not a claim that this limit exists. It is actually notation for a special kind of does not exist, that on both sides I'm growing without bound. By the definition, this limit will never exist. We're just going to write it down in this really weird way. The limit as x approaches c of f of x is infinity. What this is really saying is that when the x's get close to c, the y values grow without bound. I really wish that mathematical notation, when it was developed for this, didn't include the equals. I wish we had put an arrow there, because infinity is not a number. That shouldn't really be an equal sign. The y values are approaching infinity. They're growing without bound. We will write that later in the class when we study the material in section 2.6. For right now, we'll just say this does not exist because my y values are either growing without bound or falling without bound. And then one more kind of a limit that does not exist for now. Let's think about the function sine of 1 over x. You may have never tried to graph this function before, and it's a really kind of odd graph. So I'm gonna get my calculator out here, get out to the main screen. I'm in the radian mode. The last function I graphed was sine x over x, so I'm gonna clear that out. And this time I wanna graph sine of 1 over x. All right, so I'm gonna hit the graph button and see what happens. All right, and I can't really see what's going on there, so I think I'm gonna change my window. And it's always a good thing sometimes to play around with the window. I know sine can't be any bigger than 1 and smaller than -1, so I'm just gonna replace those and hopefully see more what's going on. And what my calculator is saying is that, I don't know, it's doing something like this, but what I'm gonna tell you is it actually oscillates more and more and more and more. Zero's not in the domain. As I get close to 0, 1 over 0 is a really big number. So sine just keeps trying to oscillate. The closer to 0 you get, is oscillating more and more and more. And because of those oscillations, the limit as x approaches 0 of sine of 1 over x is in fact not 0. The whole point is to say it does not exist. All right, so here are 3 different cases where a limit does not exist. A step function, a function with a vertical asymptote, and then this weird case where my graph is oscillating too much as x tends towards 0. All right, I hope to put this all together in the next video by working an example together.